Hello everyone, welcome back to the series on programming robot mechanics. In this video, we are going to continue with the inverse kinematics part, and we are going to extend the Newton method that we wrote previously to a vector-based Newton method. Right, so let's see what that vector-based Newton method actually means. The update equation is just the same, almost similar, like xk plus 1 is equal to xk minus f of x times f dash of x divided by f dash of x. In place of f dash of x, now we will need to compute the Jacobian matrix of f at a particular vector xk. Now, yeah, it is the same, but instead we are now going to compute a Jacobian matrix. Now, what is a Jacobian matrix? It's actually defined something like this. Like if we are given a vector function that maps from Rn to Rm, in our case, this is going to be theta, like the joint angles is going to be mapped to the space, the workspace XYZ and roll pitch yaw. Now, then we will be needing to find such a function. Now, how the Jacobian is calculated? With respect to each parameter, we need to calculate the partial derivative of the function. Now, right, so I think that is pretty much it. Now, F1 is like the first output that we get from Rm. Now, M, it is going to extend till M. So we're going to calculate it for 1, 2, 3 till M. And we're going to take each parameter along with it, x1, x2 till xm. And for this, now we need to define a partial derivative as well. Now, here is the definition of a partial derivative. It is almost again similar to that. Here we have what we do. We take in a function. We have a function that takes in many inputs, like a vector of inputs, for to say a1 till an, and we add a small value epsilon to just one of the input, assuming ai in this case, and then we subtract from the original one and divide by h to the limit h approaching 0. So this is how it is, the partial derivative is computed. Now we are going to translate everything we have written over here into some code. So let's do this. Okay, now one idea would be to extend this derivative to mean partial derivative. What we can do for that, if we have an fx, okay. Right, but we, okay. So let's have a new function called partial derivative, and then we will define the Jacobian. All right, let's do that. Now, why we are doing this and not using the original one is because we won't have the index I present in this derivative part. Like, or we can simply put I equals 0, but that won't make much sense for that. And we will need to, right, I think I is required. Now, okay. And then we will define the parameters as well like that. Now, epsilon we are going to take as similar to the previous we had. And we are going to add some documentation. Okay, now we have this, and so it's very similar to the above. Let's just first copy it and then do this. Okay, now the function that we have to input is going to be a vector function in any case whatsoever. And we are going to do something like this for x. All right, I think let's just have them. Okay. All right, we are going to import np, so it is important, and we are going to take x np dot copy x. That way we are going to have two arrays that have the same value, and we are going to adjust the xith value by adding epsilon to it. And we are going to take the calculate the actual partial derivative by taking the f of x underscore, which is the one that we adjusted, minus f of x divided by epsilon, and then return the value. Now, we are not really concerned with the input, like what should be the input and so on, because mostly these functions are going to be used by the developers and not to be exposed much to the users that are going to use the code. So that's why we can have this without checks, but it would be a good practice to add checks over here. Let's just wait for now and not add any checks at this moment. Now we are going to define, now we have defined the partial derivative. Now let's define the Jacobian method now. Now Jacobian should be fx, given an x input. Yeah, it should be something like that. And epsilon, we are going to define e1 minus 10. Let's add some documentation for it now. Let's see how we should compute this function. First of all, let's do this. Now, what are we doing in the Newton method? Derivative f dash. Okay, so what we can do, f underscore. Let's define f underscore and we will call the function at x, or maybe, let me think. All right. Okay, let's do it in this way. We are going to let's define an np.zeros matrix and define its shape 2, 3. I think it is rows, columns. Right. First we define the number of rows and then we define the number of columns. Now number of rows is going to be the output of the f, like what f outputs. And this is going to be length of x. And what we need to do is, okay. Instead, I think, okay. Let's not define this way. But if we simply start the loop, then this won't work, or maybe it will work. Right. Okay. Let's do it this way. For call in length x, for I in range length of x, we will be iterating over the x indices, and we can calculate f underscore, that is the partial derivative of f with respect to this xi. Let's do that first. Partial derivative f, we're going to take x and I is going to be the input and epsilon is going to be the same that we have passed above. Right, now we have this f value. Now this is the value of f at right. Okay. And then we can loop over this as well. And now this loop that we have, this has generated all the column wise values. Like if I can show over here. Okay, now we have just generated one column of this entire, we have generated one entire column of this, like del f1 by del x1 till del fm by del x1. This is what we have computed over here. So in this part of the code, we are going to have that. Now, one way would be to store all the values over here. That's why I had a 0 length, but okay, I think what we can do, we can have a dummy value, which we can compute. This way, now we have a dummy value of f, like what is f, what is the length of the output that f is going to return. And then we can define a value as np.zeros, rows, columns. Now rows are 1, 2 till length of m, and right. First we are going to have a length of f underscore, and then we are going to have a length of x. That way we are going to have that. And now we can simply define the value I and j. Are we doing it right? Now I will put bust and I think j comma I. That would work. X1 is changing towards the right. So yeah, x1 is changing. Yes, yeah. This is going to be something like this. And then we are going to this is value is going to equal f underscore j. F underscore j, is it going to really equal that? Yes, j is going to repeatedly change and we are going to assign all the values of f. or what we can do, instead of like looping it over here, we can simply assign the value something like this. J comma I, and we're going to assign f underscore to this. So one complete column is being assigned this value. But we select the row. Are we doing it right? We select all the rows and we select the ith column. Yes, I think we are doing right. So we can remove the loop over here. And yeah, I think this is pretty much it, and we can return the value now. Okay. Now, before moving on, I would like to test how this is working because I'm not really sure if this is working correctly. So let's define a test for it. We are going to define a new function for this. So let's define that. So this is the function that we have defined, not taking much values. We have just used the previous functions that are present above. What we are doing, we're taking in the x value, and the x should be a vector of length 2, and the output is also a vector of length 2. So finally, the Jacobian is going to be a square matrix 2 cross 2, and the output should be df1, like the derivative of function test1, because this is del f1 by del x1, and the last element should be df2, del f2 by del x2. Rest both of these values should be 0 because this function does not change when we change the value of x1. That's why it should be 0. And similarly, this value should also be 0. So we should get at x equals to some value like this, like we've calculated that above. So let's input this and see what we get the result as. Okay, now if we cannot have it at x equals to, right, we need a vector because we are taking in a vector. So we're simply going to have 1, 2. And 1, 2 will imply that that will go into 4. So yeah, that will be 5, right? Let's see how this works now. All right, one thing that we should note, we should make it a convention to always use np.arrays as such in this code. Otherwise, there will be a lot of confusion where we are using lists and where we are using like value np arrays and so on. So first, from now on, we are going to always define this np arrays. Now let's run this code. cd tests and python test.py. Let's see what we get the result. If it is correct, now it gives 0, 0. Let's see how we went wrong, or maybe our value is wrong. Let's see. All right, here was the problem. Let's see that. Now what I noticed the problem was when we were doing this np.copy x. Now since we are not using Python, instead we are using NumPy for all our calculations, like interpreting the lists and so on. NumPy wasn't allowing this plus epsilon to take place. We were adding that epsilon. Earlier, the code was something like this. Now, when we copied x, and if we added an epsilon, NumPy made no difference in adding that epsilon because it was treating it as an integer array. Therefore, we need to add this dot as type that converts the simple np array to np.float64. Even 32 doesn't work. np.float64. This way, when we add the epsilon, NumPy takes the takes the initiative to add that epsilon and give us a particular value. That's why it's converging to this value now. Otherwise, it was not at all doing that. So now let's complete the test that we had just written. 0, right. Now, what other thing that we also noticed, that using an epsilon that is not 1e minus 10 actually gives better results, perhaps. Let's see how much. Oh, the results completely changed. Let's see why is this behavior. Oh, okay. We didn't save the previous file and that's okay. No problem. All right. 2.356662, and earlier we had 62. Okay. Now it's not exactly converging to 354 for some reason. Let's add minus 15. Let's try and increase this. Let's just observe what is the behavior of this. Like increasing, decreasing, what to say, doesn't really add up to anything. Increasing certainly helps, but yeah, it is 4.99999, like very close to it. But here 354. Now it converges. Like there is some particular threshold that it works really good at, and when it crosses it, it performs poorly. When it has not crossed it, it performs really well. Like now it has 5.0001. So yeah, and but the -2 is still that thing. Now this problem is basically because of Python, because we are Python has some difficulty in storing float values. Actually, any programming language has some problem in storing the float values. Anyways, we are going to complete the test this almost equal. We're going to use the NP testing part. So let's do that. Right. So it is converging now. Okay. Instead of that and assert almost equal, we needed to use assert all close. The almost equal was for scalar values. This all close is for array values like vectors and all matrices. Now Jacobian is working. Now we are going to write the Newton method for vectors. Now this is going to be something interesting. Let's do this now. I'll just start. Okay. Now, why we put this x in it as none? Because we don't actually know what is the length of the output that this is going to give. For that, what we will do, now we certainly don't have any value related to f, so how should we compute it? Okay, this is interesting. Now the user, okay. Now either the user has to enter a size or they can choose not to enter the size, like x in it. Okay, so we need to enter that size as well. Let's name it this parameter as n. Now this is going to be required, otherwise our function won't be able to work. Okay. Input vectors. Right. Now, okay. Now if x underscore init is none, then we are going to assign x underscore init equal to np dot zeros n. Right. Now this is going to define that. Okay. Now we'll just do the same thing that we have over here. Very similar. Okay. Now we have x init plus 2 times epsilon. Okay. Let's see. How do we add that epsilon? Yeah, epsilon needs to be added to every value. Here, the previous value and the current value, all the values need to be greater than epsilon or less than or equal to epsilon in order for this loop to halt. For that, instead, absolute is okay, but Instead, now we need to use np dot absolute, and we also, let's just run it and see what the error, because we need to decide like np dot all is going to be the thing. Okay. Oh, right. Let's just first do that, and then we'll see if any error comes along or not. Now np dot all is required. Scalar like, not really sure if np dot all is going to be written over here or over here, but that's how it's going to work. Like every value should be greater than epsilon. That's how it's going to work. Scalar like axis. I think yes, it should be something like this. Okay. All the value should be then, and we have the previous value. Then we need to compute the Jacobian. Okay. Let's name it J for now, simply. And then we put in the function and then the value and epsilon. Okay, epsilon needs, we didn't even adjust epsilon over here. No. Yeah, it's all right. It's fine. Okay, now we need to calculate the inverse of J. Now, for our particular test, we are having a square matrix, but for some tests, we won't actually be able to have this a square matrix in every case. For that, we need to calculate the pseudo inverse of the Jacobian matrix that we get. For that, we need to use a particular function, and that is the function that we're going to use is np.linear algebra library, and we are going to type in P inverse, and then we're going to pass in the J. And I think it should be multiply. Now, I'm not really sure, like this is a matrix, this is going to come out a matrix, and this is going to be multiplied by a vector. If you put a multiplication over here, should this work? Let's see. Okay, we can simply use the dot function, np dot dot. But dot, wait a second, dot may not work. Yeah, dot will work. A dot dot. Yeah, dot will work. np dot dot. Right, and then we need to do this, and over here. Right, it will compute that dot product between these two values. Right, now are we going the right way? I think yes. Okay, I think it looks good. Let's test it first, and then we'll point out any errors that we have. The test is going to be very similar to the one that we have above for the Jacobian part. We're going to use both of these functions as a vector type of thing. So let's do that. Let's try and print the value. I'm really unsure if this will work or not. Okay, so the output it gave, oh, it actually gave the output, right? Okay. Now -1 is the output that it gave. Okay. Now one thing that I'm thinking, let's just not make n a parameter over here, but let's make x in it as an not an optional but a required parameter. That way, any user can adjust what the x in it is going to be. Are we right? Yeah. That way the user can. Oh, okay. We need to move this as well. Right. And okay, this looks good. That way the user can decide any value of x in it, because Newton method is quite sensitive to the initial value that we put. So that way we do not the user has some flexibility over what x in it wants. Like for this instance, x in it was 0 that we defined, and that's why it converts to -1. If we had put any other value, like over here, I think we put -5, then it converts to -2, right? Okay, so let's now put the np.testing part, and I think, and then we will add one more test. This is for a square matrix. We will add one more test for a non-square matrix, and then we would be done for this video. All right, let's do this. Now, as we saw above, in order for this to work, we need these values. Like we need to use the function assert all close. Now value is going to be minus, okay. We did not first, and we also need to pass in an np.array. The first value should be -5, similar to the above that we have, like -5, and the other should be 0. Okay, and -2 and minus 0.6845, and significant digits are going to be 4. Wait a second. Actual desired. Yeah, it is. It looks good. Okay, let's try this. Right, it works. Okay, it works. Test. Oh, actually we. Okay. You need to define this. Test Newton vector. Otherwise, the two functions names are similar. Yeah, it still converges, and it's like an 8 or 7. Like it converges really well. All right, now let's define a new test for a non-square matrix. Let's do that. All right, here's the function that we developed. Right, so what we do, I took this from the internet. We take x1 cube plus x0 cube plus x1 minus 1 and x1 cube. Yeah, you can read up all this. The solution for this set of equations, these 4 equations, comes out to be 1, 0. Right. Now let's just print the values and see how the values are coming out. Let's clear this. Now the values do come out to be 1, 0. And this is something interesting to note, that Newton method took 21 iterations other than the 7 iterations. So what this means, that the Newton method is also working for matrices that are not non-square as well. Now let's complete the test, and right, let's complete the test first. We have 1 and we have 0. All right, all the tests. Oh, one test didn't work. Let's see what the problem is. Insert all close. Well, let's see. Now, this took almost, but why didn't it take 4? Insert all close. Okay, let's try this. Okay, so instead of all close, actually np.assert or array almost equal works. Like it also has, yeah, there seemed to be some problem with assert all close. So now we're going to replace wherever we have assert all close with this, and let's see if this works. If this works, then we are done. Okay, right, where is this? Arrays are almost equal to, let's debug this as well. Oh, we once again did the same mistake, 6845 and 6485. Okay, now it is working. All the tests are working completely fine. And we are done with the Newton method optimizer. In the next video, that is, I think, going to be the final of the IK part, IK sub-series. In that, now we are finally going to write our IK algorithm that is going to use this Newton method vector function. We are going to compute the inverse kinematics using this function itself. So really excited for the next video. So see you in the next video then. Bye.